Hi everyone, I hope you're all well. Thank you very much for joining me today. If you can't hear me, or you don't understand what I'm saying, or if you've got any questions, please drop me a line in the chat. I'm going to try and monitor that as I go along. So my name is Hevin. I'm the author of Machine Learning with R, the Tidyverse, and MLR with Manning. And I'm a life science researcher working at the Francis Crick Institute in London. And today I'm going to show you how you can train, tune, and cross-validate a support vector machine model in R using the MLR package. So support vector machines are models for supervised machine learning. So performing machine learning tasks where we have some ground truth in our training data that we can compare to. And support vector machines can be used for both classification, where we're trying to predict a categorical outcome, and they can also be used to train regression models, where we're trying to predict a continuous outcome. And the support vector machine algorithm works by trying to find a hyperplane that extends through your feature space that best separates the classes in a classification task. And here is a sort of silly contrived example from my book where we measure the amount of money that you make your company, say in a given week. And you also measure the amount of time that you spend playing video games at your desk. And every day you record these two variables, and you also record whether your boss is in a good mood or a bad mood with you. And so we're trying to use a support vector machine algorithm to train a model that will help you predict whether your boss is in a good mood or a bad mood with you, which is a very important application of machine learning. And so you can see that in this example, we have two classes. This is an example of a binary classification problem. And the two classes are very easily separable. They're completely distinct from one another. And so actually there are a number of decision boundaries that we could use to separate these two classes. But the support vector machine algorithm tries to learn the decision boundary, the hyperplane, that separates your classes, but which also maximizes the margin around itself, the region around itself, for which there are no or few cases. And the reason that it's important that it does this is that this is the hyperplane or the decision boundary that is, at least based on the training data, that is most likely to generalize well to future data sets. And the support vector machine algorithm is very popular and very powerful. And one of the reasons for that is that it's actually very good at learning complex non-linear decision boundaries, which seems like a little bit of a contradiction after I've just told you that it specifically learns hyperplanes, which by definition are linear. And the way that support vector machines can learn non-linear decision boundaries is that they can take advantage of something called the Kernel Trick, where they're able to add an additional dimension to your feature space that helps separate your classes. So here is an example where we have a two-dimensional feature space, and we have cases belonging to two classes, and you can see that there is no linear hyperplane that would do a particularly good job at separating these two classes. But using a kernel function, the support vector machine algorithm can add a new dimension to your data set. And you can kind of think of this as kind of a stretching or a deforming of the feature space in a way that helps separate the classes. And so in this example, you can see that we're kind of stretching up the feature space from this original two-dimensional feature space into a three-dimensional feature space, where now the algorithm is able to find a linear hyperplane that actually does a good job at separating these two classes. And if we project this hyperplane onto this kernel function and take where it cuts this kernel function and project this back onto our original two-dimensional feature space, you can see that now we have a complex non-linear decision boundary that is able to separate our classes. And so I'm going to show you how we can train a support vector machine model in R. Okay, so for those of you that are used to working with R and in RStudio, you may know, or you may find it useful to know, that if you push Control, Shift, and R, you can enter a section label. So I'm going to start by loading packages. So I'm going to load the MLR package and the tidyverse set of packages, which are a set of packages for manipulating, cleaning, and plotting your data. And my book covers tidyverse tools in quite a bit of depth. So then we're going to load a data set, and I'm going to load the spam data set from the Kernel Lab package. And this is a data set that contains 1 row per email, and every column is a different metric or measurement made on that email. So for example, it could be the number of capital letters, whether there's a URL present, the number of exclamation marks, etc. And this dataset is a labeled dataset where some of the rows are labeled as being spam, so junk mail, mail that is not desirable, or as not spam, so genuine emails that we would be interested in receiving. It's not a massive dataset, so if I check out the dimensions, we've got 4,601 rows, so 4,601 emails, and 58 columns. That's not a massive data set, but for the sake of speeding things up today, just so that you guys aren't having to watch my computer whir away for ages, I'm going to downsample that just so we're working with a smaller data set. And I'm also going to convert it into a tibble. So you're probably used to working with data frames in R. The tibble is the tidyverse reimagining of the data frame, and it has some nice properties to it, and some of the most useful ones are that it prints your data in a nicer, cleaner way, and I'll show you what I mean by that in a second. But we could continue using data frames for the whole of this example. It's just my personal preference. Okay, so I'm going to create a new object called spam tib, and I'm going to use the sample n function to sample just 1,000 rows randomly from the spam data frame. And I'm going to pipe this. So this pipe operator takes the returned value of the function on its left and passes it as the first argument to the function on its right. And I'm just going to pass this into as tibble to convert it into a tibble. And now if I call this spam tib, then you can see that we've got a tibble with 1,000 rows and 58 columns. And you can see some nice features of how tibbles are printed here. So it'll only show the number of columns that will fit in your console, and the remaining columns are listed below. It only shows you the first 10 rows by default, and also it tells you the type of column that each variable corresponds to, so whether it's double, factor, character, logical, etc. Another useful function is the glimpse function, which kind of turns the data on its side, and instead we get kind of 1 row per column. So this is a nice way of quickly seeing all of the columns that you have in your data set, and it shows the first several values for any of your variables. And if I come right to the bottom, you'll see that we have this variable at the end called type, which is a factor which has 2 levels, either spam or non-spam, as our labeled data. And actually it would be useful for us to get an idea as to the proportions of those two categories that we have. So I can call table on spam tib and the type variable. And I can see that in this data set, I have 596 non-spam emails and 404 spam emails. Okay, so in order for us to train a model with MLR, we need to first create two things. We need to create our task, and our task is just a definition of the data set that we're working with. And if it's a supervised machine learning task, it also includes a definition of what our target variable is going to be, so which variable we want our model to predict. The second thing that we need is to define a learner, and the learner in MLR is simply the definition of the algorithm that we're going to use to train the model, in addition to any additional options that we might want to supply to that algorithm. So define task and learner. So my spam task is going to be so this is a classification task because we are trying to predict a discrete category, spam or not spam. And so the function to create a classification task is make classif task. If this was a regression task and we were trying to predict a continuous variable, then it would be make reg task. If this was a survival task, make serve task. If it was a cluster task, make cluster task, etc. So this is a classification task. And we first give the data, which is our spam tibble. And as this is a supervised machine learning task, we also have to provide an argument as the target. And this is the name of the column that we're trying to predict. So this, in this case, is the type column. Of course, if this was an unsupervised machine learning task, such as a clustering task where there is no target variable, we simply omit the target argument because it doesn't make sense to supply one. So when you create a task, you'll get a warning that basically just says that the data that you provided is not a pure data frame, but is of class Tibble data frame. This still works. It's just warning you because it expected a data frame and it got a Tibble instead, but you can safely ignore this warning. Okay, so now I'm going to create my learner. I'm going to call my learner SVM for support vector machine. And to make a learner, we use the function make learner. And MLR comes with a large number of machine learning algorithms already built in, and you can define your own if the one that you want is not implemented. And they follow a particular naming scheme where every learner has a prefix and a suffix. And the prefix just tells you whether it is a classification, clustering, regression, or survival task, etc. And then the suffix is the name of the algorithm, or it is usually actually the name of the function from the package that the algorithm is derived from. And in between the prefix and the suffix, the name just has a period. So for example, for today, the name of our learner is going to be classif.svm because it's a classification task and we're going to use the support vector machine algorithm. This might seem a little bit overkill, but as a number of algorithms can be used for both classification and regression, such as the SVM algorithm, it's important to tell MLR which variant you're intending to use. There's another an optional argument which I recommend, which is predict.type, and I recommend that you set this to prob. So the default for this argument is that actually, what is the name of the default? Make response. That's it. Okay, so the default is response, and what this means is that models that you train using this learner definition, if the predict type is set to response, when you use that model to make predictions on new cases, on unseen data, the model will simply spit out the most probable class for that data. So if we were to pass some new emails through the model that we're about to train, it would just say spam, not spam, without giving you any quantifiable measure of how confident the model is that that email was spam or not. And so for models that support it, or for algorithms that support it, I recommend setting the predict.type argument equal to prob. So now when you make predictions on new data, rather than just getting spam, not spam, the model will actually return the estimated probability that it thinks that case belongs to a particular class. And this helps you make better decisions, because one email could be given a probability of being spam of 0.9, so very confident that the email is spam, and another could be given a probability of 0.51. And if all the model gives you is spam or not spam, you don't have the kind of information to help you make better decisions. So you may, for example, want to treat those probabilities closer to 0.5 slightly differently. You may want to manually annotate those cases, for example. So we're going to set predict.type to prob. Okay, so the next thing that we're going to do is define our hyperparameter search space. So a hyperparameter is a setting or an option or a variable that controls how an algorithm learns a model, but that cannot be estimated directly from the data instead. And the SVM algorithm has a number of hyperparameters that we need to set. And one way to set them would be to, for example, pick values that seem sensible to us or that have worked well for similar problems in the past. But a more sensible way is actually to incorporate a tuning procedure during model training and allow the model to filter out and find the best performing combination of hyperparameters automatically. And so what we first need to do in order to do that is to define our search space of hyperparameters, basically our set or a combination of possible hyperparameter values that we want to search over in order to find the best combination. Okay, so for any given algorithm, you can find the available hyperparameters for it by calling the get param set function and providing the name of the learner. If I expand this out, so you can see that you get a data frame where every row corresponds to a particular hyperparameter. We get the type, so whether it's a discrete hyperparameter or numeric or logical. We get the default values. So for example, the default of this cost hyperparameter is 1. We get the constraints, so the upper and lower bounds, if it has it. So for example, the cost is constrained between 0 and infinity, and whether that particular hyperparameter is tunable or not. So the most important hyperparameters of the SVM algorithm for us to tune are the cost, the kernel, degree, and gamma. Have I missed anything out? No, those guys are the most important. So what do I mean by those? Okay, so I mentioned here that support vector machines are kernel methods. They can use kernel functions to deform and stretch the feature space to help separate classes. And there are a number of different kernel functions that will deform the feature space in different ways and that may be useful in different situations. And so here are some examples of some of the most common kernel functions. And choosing as the kernel function can't be directly estimated or our choice of kernel function can't be directly estimated from the data, the kernel function that we use to train the model is a discrete hyperparameter. And so we have to, during our hyperparameter tuning process, get the model training process to select the best performing kernel. So we have the linear kernel, which is actually equivalent to no kernel at all. We can use polynomial kernels, which will learn decision boundaries of increasing flexible complexity. So as you increase the degree of polynomial from second to third to fourth, etc. And if we choose the polynomial kernel, then the degree of that kernel is also an additional hyperparameter that we would tune. The radial basis kernel function is actually the default, and this is kind of shown in this example here actually. And the radial basis kernel function is very good at learning or deforming the feature space in such a way that it helps us to form decision boundaries between clusters of cases that may be surrounded by other classes, for example, or that are discontinuous from each other, as in this example. Or another example of a kernel function that is useful when you have one class that is maybe bounded by another class or other classes is the sigmoid kernel function. The cost hyperparameter tells the algorithm how bad it is to have cases inside the margin. So when I gave you this example earlier on, and I mentioned that support vector machine algorithm learns the hyperplane that maximizes the margin around itself, that's true in easy examples where the cases are completely separated. But if you're working on problems as easy as this, then actually support vector machine algorithm is probably overkill for you. For more complicated real world examples, it's very rare to have margins that have absolutely no cases inside them. And so really, when we talk about the SVM algorithm, most of the time we're actually talking about soft SVM, which means that actually it does allow cases inside of its margin. And how bad it is to have cases inside the margin depends upon the cost hyperparameter. So if cost is low, then the model doesn't really mind that much when there are lots of cases inside the margin. And what this means is that if your cost is too low, the algorithm may learn a decision boundary which actually is quite insensitive to local changes near the decision boundary, near the separation between your two classes. And so if the cost is too low, then you may end up underfitting your model. If cost is high, then the model considers it to be very bad to have lots of cases inside the margin. And so what you tend to have is the algorithm learning a decision boundary that very harshly fits the noise perhaps near the boundary between the two classes. And so there's this trade-off between setting your cost too low, in which case you may end up underfitting, and setting your cost too high, in which case you may end up overfitting. There's a similar consideration for the gamma hyperparameter. So the gamma hyperparameter you can kind of think of as how attention-seeking each individual case is in the data. So if you imagine all the cases kind of vying for attention, shouting, classify me correctly, then gamma hyperparameter is how loud they all shout. And so if your gamma is too low, then your algorithm doesn't really place too much importance on learning a hyperplane that correctly classifies all of the cases in the data set. And so if you set it too low, again, you may learn decision boundaries that are too general and underfit your data set. If you set gamma too high, then the opposite is true. The algorithm really puts a lot of emphasis on learning decision boundaries that will try to classify all the cases correctly. And what you end up getting is decision boundaries that are very granular and very overfit to the training set. Okay, so in order for us to automatically tune our hyperparameters during training, the first thing we need to do is define our search space to tell the training algorithm what possible combinations of these hyperparameters we want to select to try and validate. So I'm going to start by defining a vector of the kernels that I want to try. So we are going to try the polynomial, radial, and sigmoid kernels, and notice that I've omitted the linear kernel, but that's just because we are also going to tune the degree hyperparameter, the degree of the polynomial, and I'm going to include the first degree polynomial in that, which of course is just the linear kernel. Okay. So I've defined a vector of my kernels, and now I'm going to define SVM param space. And in order for us to define a hyperparameter search space, we use the function make param set. And in this function, we simply provide a definition of the hyperparameter that we're going to tune. And we define either a set of plausible values or perhaps an upper and a lower limit. And we simply separate each of these hyperparameter definitions by a comma within the function. So the first one I'm going to do is I'm going to define our kernel hyperparameter, which is a discrete hyperparameter. It can only take one of these three values. So the function to create a discrete hyperparameter is make discrete param, and the name of the hyperparameter, as we got from this table, is kernel. And its possible values are equal to kernel, this vector that I defined here. Actually, that's kernels. Okay, so that's my first hyperparameter. The second one I'm going to define is the degree hyperparameter, and this will only really matter as and when the search process selects polynomial as the kernel. Otherwise, this particular hyperparameter has no effect on the radial or the sigmoid kernels. So the degree hyperparameter is it must be an integer because it's the degree of the polynomial, and I'm going to define this to be between the values of 1 and 3. So I'm going to use the function make integer param. This is the degree, and I'm going to define the lower bound as 1 and the upper as 3. The next hyperparameter I'm going to define is cost, which is a numeric hyperparameter. So the cost can take on floating point decimal values, and so I'm going to use the function make numeric param. This is cost, and the lower is equal to 5 and the upper is equal to 20. And you might be wondering why I've selected these values, and it's partly because I've run this example before, and I know that these values work well, but frankly, when you're training hyperparameters, start by setting the net relatively wide and use some of your knowledge as to perhaps what you've tried in the past for similar problems. Start by casting your net wide, and actually I probably won't show you today, but actually it is quite important to plot your hyperparameter tuning process to ensure that you are at a minimum, hopefully the global minimum in terms of the loss during your model training. But you want to make sure that, for example, if you didn't continue going higher or lower with a particular hyperparameter value, that you wouldn't get better performance. But for the cost today, I'm going to bound it between 5 and 20. And then finally, I'm going to define the gamma hyperparameter. So again, make numeric param gamma and the lower is equal to 0 and the upper is equal to 2. Okay, so now I've got my definition of the hyperparameter search space. I now need to define actually how this search space is going to be explored or sampled during model training. Okay, so when we're training the model, we are basically going to end up training the model many times, each time using a different combination of hyperparameters. And there are different ways that we can select combinations of hyperparameters to try and then to validate their performance. One common way is to use what's called a grid search, which is to take every, from the definition of our hyperparameter search space, take every possible combination of all of those hyperparameters and tune a model, and train a model using that combination of hyperparameters, and then evaluate the performance of all those models and pick the one combination that results in the best performing model. And that is the only search method that is guaranteed to find the best performing combination of hyperparameters within your search space. Okay. The problem with it is that unless you have a small number of discrete hyperparameters, then actually the hyperparameter search space blows up to a massive size, and you could end up having to train millions of models. And actually in this example that I've defined here, we basically have an infinite number of combinations of these hyperparameters because I have numeric parameters in there that can take on floating point decimal values. And so in this situation, a grid search is really not appropriate. But let's say, for example, you only had 1 or 2 discrete or integer hyperparameters, then you may prefer a grid search because it's guaranteed to find the best performing combination within the bounds that you've defined as your search space. A more pragmatic approach is to perform a random search. And for a random search, during model training, we simply randomly select a combination of hyperparameters and we train a model with that combination. And then when we train the next model, we again randomly select another combination of hyperparameters and we train a model on that. And we do this for a fixed number of iterations, basically whatever our computational budget is. And of all of those sampled combinations up to the maximum number of iterations, we then find the combination that performs the best. Okay. And of course, this method is not guaranteed to find the best performing combination of hyperparameters in your search space. But the more iterations that you have, the more likely you are to come up with the best performing combination. And so this is what we are going to use today. So I'm going to define an object called rand search, and the function that I use to define this is make tune control random. And if I was performing a grid search, then this would be make tune control grid. There is another option which is make tune control iRace, which uses the iterated frace algorithm for trying to find the best combination of hyperparameters. And this is kind of a happy intermediate between the grid search, which may be impossible, and a random search. So it is more likely to find the best performing combination of hyperparameters than a random search, but will still take longer than a random search, depending on the number of iterations that you apply for a random search. But for today, we are just going to define make tune control random, and we need to define the number of the maximum number of iterations that we want to perform. And again, you should set this based on your computational budget, but for today, just for the sake of saving some time, I'm going to set this to 20 iterations. Okay, so the next thing that I'm going to do is define how I'm going to evaluate the performance of my model training process, and how I'm going to evaluate the performance actually of each of these models trained on different combinations of hyperparameters. And I'm going to do that with a process called cross-validation, and more specifically I'm going to use a technique called nested cross-validation. Okay, so what is nested cross-validation? Okay, so if you've done any sort of machine learning in the past, there we go, sorry. So if you've done any sort of machine learning in the past, then you will probably have come across the whole paradigm of training set, validation set, and test set, where in order to get an idea of how your model will perform on future unseen data, it's extremely important that you don't evaluate its performance on the data that you used to train it in the first place, because models will almost always perform better on the data that you use to train them than on new data. And so commonly what people will do is that they will split their data into a portion that they'll call the training set, and these will be perhaps randomly selected rows that the algorithm has access to during training, and they'll train a model on the training set. And then they'll take that model and they'll evaluate it on another partition of the data called the test set. And the test set arose from the data that the algorithm did not see during the model training process. And they'll, in a supervised machine learning setting, they will get the model to make predictions on the test set, and we'll compare those predictions with the ground truth, and we'll report some kind of metric that helps us evaluate how well the model has performed. One of the simplest for classification being the accuracy of the model. What proportion of cases did the model correctly classify, for example? And sometimes what people will also do is they will have a third set or partition of their data set that they will call the validation set. And what they will do is they will train their model using the training set, perhaps using one combination of hyperparameters or some kind of settings or options for their model training process. They'll train that model in their training set, and then they'll evaluate it on the validation set. And then they'll tweak and they'll change those hyperparameters and train a model using the training set, and then evaluate it on the validation set. And keep doing that, training on the training set, evaluating on the validation set, until they feel that they have a combination of hyperparameters that they think works the best, gives the best performance on the validation set. And then once they have that, they will then evaluate their model on the test set, which has not been seen by the algorithm at any point during this model training and tuning process. And they will use that then as a sort of final metric for how they believe that their model will perform on new data. And if you've got an algorithm that is computationally intensive, or if you've got a situation where you have a very large data set, and so the performance metrics that you get back are actually quite robust and don't change from time to time, then actually this paradigm of training set, validation set, test set is very robust, and it works well, and many people do it. But if you have the computational budget, or if your the number of cases that you have is quite small, then I prefer to use nested cross-validation instead. And so let me just go through it and explain in a little bit of detail, so hopefully it'll make more sense. So in this example today, what we're going to do is take our data set and split it into 3 folds, okay, just like k-fold cross-validation. And we're going to reserve 1 fold as our test set, and the other 2 folds we're going to further split into a training set and a test set. Okay, so we've got this kind of outer partition where we have 3-fold, and we have this inner partition using just the training set, which is actually just simple holdout cross-validation, okay, where we have 1 portion as the training set and 1 portion as the test set. And then using this data, we're going to, using our random search procedure, we're going to randomly select a combination of hyperparameters from the search space that we defined, and we're going to train a model using that combination. And then we're going to evaluate that model on this test set. Then we're going to do the same thing again. We're going to randomly select another combination of hyperparameters, train a model on the training set, evaluate it on the test set. And then we're going to keep doing that all the way for our 20 iterations that we defined. We were going to only do 20 iterations of our random search. And then at the end of this, we've got 20 models all trained and evaluated with 20 different combinations of hyperparameters. And we're going to take the model that gave us the best performance on its test set, and we're going to pass that winning combination of hyperparameters up to the outer loop. So this is the inner loop, and this here is the outer loop. Then we're going to train a model using using this training set, using that winning combination of hyperparameters, and then we're going to evaluate it on the outer test set. And then we're going to do that whole procedure twice more, where this time we're going to use this middle fold as the test set, and we're going to derive our inner loop using this block and this block. Okay, and then again, randomly select hyperparameter, train a model on the training set, evaluate it on the test set, and do that for all 20 iterations, pass the best hyperparameter combination up to the outer set, and then we'll train a model using those hyperparameters using the 2 training set folds and evaluate it on the test set fold. And then we do that again finally, where now this fold is reserved as the outer test set. And so what we end up with is, instead of just 1 measure of model performance on 1 test set, we have 3 measures. Okay, and then what people will usually do then is take the aggregate or the mean performance measure across those models, and this has a couple of advantages over the simple training validation test set paradigm. One of them is that we're not just relying on a single test set for our evaluations, because of course it could be that by sheer chance, especially if your data set is small, that you picked a partition of training and test set that meant that the test sample was quite easy for the model to classify, whereas in this case we're using all of the data as the test set at least once. The other advantage is that although we're not doing it in this example because we just have simple holdout as our inner loop, but if you did something more sophisticated as your inner loop, say for example we also did 3-fold cross-validation on the inner loop, it actually means that you have a moving validation set, so that you're not just reusing the same validation set over and over and over again, because of course you can end up overfitting to your validation set, although we're not doing that today. Of course, the one big downside of this is that you end up actually having to train your model 3 times more than if we just did simple training, validation, and test set. Okay, so that might seem relatively complicated, and in a way it is, but thankfully MLR makes this very simple and very easy for us to define. So the first thing that we need to do is define actually what our inner and outer cross-validation loops are going to be. So in that example that I just gave you, our inner cross-validation strategy is simply holdout, where we just reserve a proportion of the rows as our test set. And the outer cross-validation loop is going to be threefold cross-validation. So I'm going to define my inner using the make resample desc function, so for make resampling description, and this is going to be simply holdout, and the split corresponds to the proportion of rows in the data that you're going to reserve as the training set. So I'm going to set this as 2/3, so that this ends up being 2/3 of the data used for training the model, and the final third used as the held out portion for validating its performance. That's my inner, and then for my outer, again, make resample description, and this is going to be CV, which means k-fold, and the number of iters is 3. So this is threefold cross-validation for my outer loop. There are some other resampling strategies that we could have used. So we could have used, so instead of holdout or CV here, we could have used LOO for leave one out, which is the extreme of k-fold, where you train a model using all of the cases and then except one, and then evaluate it on that one. And you do that for every single case in the data set. We could have also used, this is particularly useful if you have a very small data set, rep CV, which is repeated cross-validation. So for example, we could perform this threefold cross-validation once, then we could jumble up all the rows and randomize them, and then we could perform threefold cross-validation again, and we could repeat that for as many iterations as we wanted to, or we had budget for. This is useful for small samples because actually you end up with many more different combinations of cases in the training and the test set. And then finally, we could also use subsampling instead. Okay, so in order for the algorithm to automatically tune the hyperparameters for us, we have to wrap together the learner and the hyperparameter tuning process. So we're going to define a wrapper. So I'm going to define an object called SVM wrapper and use the function make tune wrapper. So what we're doing is we're creating a new learner that is kind of a fusion of an existing learner and a hyperparameter tuning process. And so what will happen then is that when we ask MLR to train this learner, it will perform the hyperparameter tuning process as part of the model training process for us. Hopefully it will make more sense in a second if it doesn't already. So first we give it the learner, which is the SVM learner that we defined here. We give it the resampling strategy, which is our inner cross-validation strategy. So this is what is going to be used to cross-validate each individual combination of hyperparameters. So remember, we are here and this is the inner loop. This is our holdout that we're going to use to cross-validate each of these combinations. The par.set is the hyperparameter search space that we defined. So this is SVM param space that we defined here. And control is the search method that we defined as the random search, which is here. And this is now my wrapped learner. So it's a learner, but it also includes hyperparameter tuning as part of the algorithm. Okay, so now what I'm going to do is run my cross-validation strategy to hopefully give me an idea of how this approach that I'm taking to model training will hopefully generalize to future data. Okay, so I'm going to define an object cross-validation with tuning, and to perform cross-validation with MLR you use the function called resample, and we give it the learner, and this learner is my wrapped learner that we just created here. The task is the spam task that we defined earlier to tell us what our data and what our target variable is. Our resampling method is the outer cross-validation loop, which is our threefold cross-validation. And there's an additional optional argument I'd recommend that you set, which is models equals true. So the default for this argument is false, and the resampling, the cross-validation procedure will then simply return you the performance metrics, and it discards the models. It doesn't save the models, where actually sometimes it's useful for you to keep the models so that you can interrogate them. So I'm going to set this to equal to true. And so if I run this, this is now performing my nested cross-validation. So at the moment we are on this first outer fold, and you'll see that the algorithm is selecting a combination of hyperparameters, training it on the training set, and evaluating it on the test set. And then once it's done that 20 times for a particular fold, it will then pass up the winning combination to the outer loop. We'll train a model using the training data, using that combination of hyperparameters, and then evaluate it on the test set. And for classification tasks in MLR, the default performance metric is the MMCE, or the mean misclassification error, which is simply 1 minus accuracy. If you've spent much time reading about performance metrics in machine learning, you'll know that actually accuracy is often not a good measure of model performance, but for today, as our classes are relatively balanced, it's fine for our purposes today. And so you can see now that it tells me that the aggregated result is an MMCE, so a mean misclassification error, mean of 0.088942. So if I take this and I do 1 minus, basically we have an accuracy of 91%, which isn't bad for a first go. And so this is the mean of the MMCE values for each of these three folds of our outer cross-validation loop. And if I want to, if I call this object that we just saved and extract the measures.test, then you can see I can get the individual MMCE values for each of those folds of my outer cross-validation loop. Okay, so 91% isn't fantastic, but let's pretend for argument's sake today, that I'm happy with that level of performance, and so I am going to train a final model using all of my data, using this same approach that I've just taken here now, because once you cross-validate your model training process, it's important for you to then train your model using all of the data available to you, because models trained with more data will have less bias. So train model using all data. So again, I'm going to tune the hyperparameters, because when we cross-validated the model training process, we weren't cross-validating a single model. We were cross-validating the process of training the model in using that particular approach. And so I'm going to tune the hyperparameters again, but this time using all of the data available to me. And so I'm going to define an object called tuned SVM parse. I'm going to use the function tune params that will actually just it is a function purely for the tuning process. So this will return the optimal combination of hyperparameters that I can then use to train a model using all of the data available to me. So again, the learner is equal to SVM. My task is spam task. The resampling, because of course you have to have some kind of way of splitting your data in order to evaluate the performance of each hyperparameter. So I'm just going to use my inner cross-validation strategy, which is simply holdout. My parse set again is my parameter space that I defined, and the control loops is my rand search. Okay. So then when I run this, it's now going to 20 times select a random combination of hyperparameters, train a model using that combination on the training set, and evaluate it on the held out test set. And then at the end, it tells me that the result is that the best performing kernel was polynomial of degree 1, so actually just the linear kernel, no kernel at all, with a cost of 20, gamma of 1.18. And this is the particular MMCE that we got, but I won't really pay too much attention to that. One thing that should be a slight red flag is that the best performing cost parameter was 20. And if I look back up here where I defined my hyperparameter space, 20 was the upper limit for this parameter. And so this would make me worry that actually I've not defined my hyperparameter search space correctly, and actually perhaps I should have included larger values. Though what I would usually do is spend time properly plotting my performance metric against all of the values of the hyperparameters, and see whether actually even at 20 my mean misclassification error was still decreasing, for example, and then adjust my parameter space accordingly. But for now, I'll continue anyway. And so actually, if I print out this, then again you can see I get this. So this that we performed was simply the tuning process, and all this returns is the best combination of hyperparameters during that random search that we undertook. And so now what I'm going to do is train a model using all of the data, using this combination of hyperparameters. And so to do that, I'm going to define an object called tuned SVM and use the function set hyperparse, and I'm going to use the SVM learner, and I want it to use the parameter values that we just tuned. So this is tuned SVM parse x, which is simply a list of the optimal values. Well, this isn't actually 20. Okay, it was rounded, but still. So what this will do is create a new learner by simply taking our SVM learner and assigning it this combination of hyperparameter values. And this is now a new learner that we can train. And to train, we simply use the train function and we give it the learner, which is our tuned SVM, and the task. And this is now training the model using all of the data and using this combination of hyperparameters. And this will take a couple of seconds. So that's our model trained. And so now at this point, our model is available to us to make predictions on new data. I don't have any new data prepared, so actually I'm going to be lazy and just make predictions on the training data, which of course you would never normally do, but let's just imagine, for example, that this is some fresh data. So we use the predict function and we give the name of our model, and the new data argument is where we supply the new data that we're making predictions on, and this data should have all of the columns that were used to train the model. So if I do this, then we get the prediction for 1,000 observations, and as the data that we passed to the predict function already had the column type, which is what we were trying to predict, it actually tells us the truth. So it tells us whether it was spam or non-spam, and it tells us the response from the model. So whether the model is predicting spam or non-spam. And remember that way back when we were defining our learner, I said it was useful to set the predict.type argument to prob, and we can see that that's paid off here, because basically now instead of just getting the response, we actually get a probability or a pseudo probability of that particular case being in each of our classes. So the probability of being spam and not spam. And there aren't really any ambiguous examples here, but that's useful because, for example, if you had an email classified as spam that had only a 0.51 probability of being spam, then you might be a little bit more suspicious about those predictions, and you may want to handle them yourself. Okay, so that is all I wanted to cover today. So let me just summarize what we've done. So we defined, well, we loaded our data set that contained one row per email and one measurement on that email per column. And the data set was labeled with whether each email was spam or not spam as a ground truth. And we used the support vector machine algorithm to train a model to try to predict whether an email would be spam or not. And the first thing that we did was to define a task, which is a combination of the data and, in a supervised setting, which variable is our target variable that we're trying to predict. And we also defined a learner, which is simply a definition of which algorithm we're going to use. And that these have a naming scheme that follows a prefix and a suffix to tell us what algorithm is available to us. We defined our hyperparameter search space. We defined our search procedure, which was random search. And then we defined our nested cross-validation procedure. And then we cross-validated our model training procedure to get an idea as to how models trained using this procedure would generalize to future data. And then once we convinced ourselves that we were happy with how our model was going to perform, we tuned the hyperparameters once again, but this time using all of the data. And then we trained the model using all of the data, using that tuned set of hyperparameters, and we made some predictions using that model. So that's what I wanted to cover. If you're still with me, thank you very much. I am happy to hang around for a little bit if you have any questions, or if you can't think of any questions now, then please feel free to add me and tweet me on Twitter. My handle is HRJ21. I'll just actually pop that in the chat. I'll hang around for a couple of seconds because the last time I did this, I stopped my stream and there seemed to be a lag, so it cut me off halfway while I was speaking. So I'll hover around for a second, but I hope that you guys have a nice rest of your day. Thank you very much.